Hello everyone. Today I'm going to present my AAT Tech Talk of Big Data and Analytics, and my topic is Domain-Oriented Software Defined Computing Architecture. So let's begin with the introduction. My title once again is Domain-Oriented Software Defined Computing Architecture. So we are going to focus on addressing the limitations of traditional architectures, especially in data-intensive fields like IoT, AI, and big data. So with the introduction of software-defined hardware by DARPA Electronics initiative, software definition will be basic attribute of information system, benefiting from boundary certainty and algorithm aggregation of domain applications. Domain-oriented computing architecture has become the technical direction that considers the high flexibility and efficiency of information system, aiming at the characteristics of data-intensive computing in different scenarios, such as IoT, that is Internet of Things, big data, artificial intelligence. We are going to discuss the domain-oriented software-defined computing architecture. So in this, we will have hierarchical interconnection structure or hybrid granularity computing elements and its computational kernel extraction methods. And that's the main thing we are going to discuss. So a domain-oriented software definition computing architecture is proposed in the way such that how new architectures addresses the performance, flexibility, and power efficiency. These three main attributes are implemented in this domain-oriented software. So first of all, we'll see why we are required of new computing architecture. So traditional bottleneck. The limitation of von Neumann architecture, especially its sequential processing model, leads to well-known von Neumann bottleneck. So we are going to use traditionally, that is sequential processing model, which requires a large amount of time to be processed, and we require it to be reduced because the increasing data, because of the new technologies such as IoT and AI, the amount of data to be processed is going to be increased exponentially day by day. So to overcome this, we are going to implement this domain-oriented software. So what are the challenges we are facing through this traditional method, that is von Neumann architecture? Rising data processing needs from IoT, AI, and big data, as we discussed. Slowing of Moore's law, necessity new performance strategies. So the Moore's law, that is the throughput and the system's performance of computing architecture, keeps on improving. However, as the semiconductor processors approaches the silicon-based limit, Moore's law begins slowing down and slowly relying on process to improve performance, that is encouraging bottleneck through the traditional methods. So with the extensive application of information technologies such as IoT, big data, and AI, the data resources and information infrastructure is explosively growing. The mismatch lead to the technology and industry reforms. Frequent data exchange in von Neumann architecture causes a large amount of power wasting on the bus and restricts the speed of information processing. So which results in the famous von Neumann bottleneck, which we have already discussed. So we'll move to the new approach, that is domain-oriented approach and software-defined hardware. So first of all, we'll see what is domain-oriented computing. So tailoring computing architectures to specific application needs, such as AI and IoT, for optimized efficiency, that is domain-based or domain-oriented approach of computing. How software-defined hardware will help here. A dynamic approach where hardware configuration adapt to different computational tasks. This is where software-defined hardware comes, mostly which includes cloud computing. The amount of or the resources that we call as hardware required for any functioning of a industry or a company may be dynamically changing due to the change in the data generated through the company or the organization. So for that, the dynamic hardware configuration, which can adapt the changes in the data generation, is required to perform better computational tasks. So let us discuss what are the key components of domain-oriented architecture. There are three main key components of domain-oriented architecture. They are hierarchical interconnection structure, heterogeneous granularity, computing elements, and data flow-driven parallel execution. So first key elements, that is hierarchical interconnection structure. That is expandable 2D mesh topology for efficient communication. SDI, that is software-defined interconnection for adaptable connections. Next comes our heterogeneous granularity, that is flexible design to support various computation intensities. Next, that is data flow driven parallel execution. We have seen that in Van Neumann architecture, we have serial execution. So in this, we'll try to implement parallel execution, combines control and data flow model to maximize parallelism. So let us discuss one by one. So hierarchical interconnection structure uses SDI, which we have already seen here, that is software defined interconnection, which is for local communication, and 2D mesh for global communication. What are the benefits of using this? Dynamic topology adjustment for power efficiency, scalability to accommodate more complex tasks without compromising speed or energy efficiency. Next comes our heterogeneous granularity, computing element. So computing elements designed based on task requirements. Next comes our customizability. That is very important. Elements can be isomorphic or heterogeneous based on the requirement, tailored to specific data processing tasks for higher efficiency. How we are going to implement based on the on-demand scaling based on resource needs, which we have already seen using cloud computing. Next, but very important, that is data flow driven parallel execution model. So what is execution model? Instructions execute when data is ready, maximizing parallel execution. So what are the advantages of it? Improved instruction level parallelism. That means multiple tasks can be run parallelly so that the time required will be reduced. Enhanced utilization of thread and instruction parallelism within programs, so that multiple request response can handle easily based on this thread, and utilization of utilization of resources will be more efficient if we use these threads and implement this parallel computing to increase our processing and will reduce the time taken to process. So let us see where the experimental comparison. So video copy detection platform compared to a general purpose server. These two are compared. So what were the results? Domain-oriented architecture outperformed general server by a very large amount of time, which can be a lakh times more better in performance, and efficiency, which is 150 to 300 times more better than the task requiring real-time data processing. So this is a huge difference made by these data-driven or data-oriented architectures or domain-oriented architectures. So what are the advantages of using these data-oriented architectures, and what are the future work which we can implement using this? So improved flexibility for domain-specific applications, such as we have discussed. This type of architecture are designed based on the domain which we are going to use, such as AI, IoT, big data, or any other field or domain, so that the data generated will be calculated according to the domain which we are going to specify. Scalability and energy efficiency tailored for future computing needs. As we are seeing the exponential growth of the data in these domains, the energy efficiency is a very important task that will be achieved by the third, that is data flow, which we are using parallelism, and also transmission, that is global and local communication, which we are using The first one which we have discussed, hierarchical structure. Next come our future work, which we can work on expanding applications across domains like autonomous driving, real-time data processing, and advanced AI. Like we have discussed already the IoT thing and AI thing. So where these are implemented in real time, like auto driving, we can say real-time data processing in healthcare, we can see, or in banking sector for approval of loan, or it may be any application of bank or healthcare or any other company which requires processing of multiple data or a large amount of data to produce an output. And advanced AI, which we are seeing, like chat GPT and other technologies which require processing of a large amount of data to result or to output a query posed by a user. Development of co-programming models for seamless software hardware integration. So now when the hardware which we are using to overcome the problem of efficiency and as well as the dynamic hardware implementation, we are using the cloud computing. So it requires a smoother communication between the software and hardware integration. So this can be worked by designing or developing the co-programming models which can seamlessly improve this software and hardware integration for the better performance and communication between software and hardware. So as we have seen that with the emergence of new applications, there are growing demands of computing capabilities from images, speech recognition to pilotless automobiles or beating the top IGO players and all. So we are experiencing the era of explosive growth of data in demand for visual data computing and understanding it. So this type of interconnection is developing quickly for people to people and things, as well as versatile things to things. It may be people to thing, people to people, or things to things based on the IoT and AI type of domain which we are using. To meet this demand of large data concurrent online processing, we must get rid of the bottleneck of the traditional von Neumann architecture, which we have already discussed, and create a highly efficient computing architecture that can be applied in different fields and has enough flexibility as the key components which we are using to overcome this bottleneck problem of von Neumann architecture. A domain-oriented concept is presented and a software-defined computing architecture for extracting basic computing elements are proposed, can be proposed so that the flexibility and efficiency of this architecture are verified by experiments. Like we have seen how the efficiency and performance increased up to hundreds and lakh times respectively, which we have seen. So to conclude, the domain-oriented architecture or software-defined computing architectures provide a flexible, efficient solution to challenges posed by traditional computing models. Embracing this model could pave the way to new era of high-performance computing tailored to demand of modern applications. By this, I want to thank you.